the organizers, and thank you all for surviving 4 lectures. It's I know it's a challenge. I want to talk today about what I call Milnor and Tiurina numbers, and formulate a number of conjectures about normal surface singularities. So let's start off, as I always like to do, with an example. Suppose I want to consider a hypersurface in Cn now, which is going to be an isolated hypersurface singularity, v comma 0, but of arbitrary number of variables, and again, isolated critical point. And I want to define 2 numbers. One is the Jacobian algebra, which is the quotient of the power series ring modulo the ideal of partial derivatives, and the Tiurina algebra, which is the quotient by the same partial derivatives, but also by the defining equation f. So these are algebras of geometric significance, but first let's just look at them. The difference is you factor out by more. Let's call the dimension of this algebra mu, and call the dimension of this tau. So we'll see later what the meaning, geometric meaning is. Again, this is a Milnor number and Tiurina number. So it's not too tough to see that mu is greater than or equal to tau. And mu equals tau if and only if f belongs to the ideal of partial derivatives. So in the weighted homogeneous case, according to Euler's formula, you write f of, for a homogeneous polynomial, f of tz naught through tzn is t to the d of f. Then you differentiate with respect to t, set t equal 1 and characteristic 0. You conclude that f belongs to the ideal of partials. The same thing works in the weighted homogeneous case. So f weighted homogeneous implies mu equals tau. So for quasi-homogeneous singularities, these 2 numbers are equal. But in fact, there's a beautiful theorem of Kyoji Saito from 1971, which proves the converse. Mu equals tau implies f is quasi-homogeneous. So in general, so we have this inequality, mu greater than or equal to tau, and it's equal, well, I can put if and only if, including the well-known result. So the only thing I'll say about this proof is that if f is summation ai df dxi, it means that here's an interesting derivation. That's a derivation of the local ring of C of zi mod f. Right? So if this is true, then d of f is a multiple of f. You take this derivation and you look at its action on the maximal ideal on m mod m squared, and derivations have to do with automorphisms, and so this is the special part. In proving this, you start off with an interesting derivation. Okay, so this will of course be the Euler derivation if it really is weighted homogeneous, and you want to prove that that's the case over here. So anyway, that's what Kyoji Saito did. Now I mentioned that these guys have geometric meaning. They're not just some numbers. So first of all, we'll start with geometry. So what's geometry? Well, we talked about the semi-universal deformation. So what's the semi-universal deformation of V look like? Semi-universal deformation. Well, that's actually going to have a parameter space that's of dimension tau. You can just write it down. You look at f plus summation ti gi equals 0. I goes from 1 to tau. you think of this as sitting in Cn plus 1 cross C upper tau, and you map this down to C upper tau by sending things down to the TIs. So what are the G's? Well, the G's, you take a basis, you take a bunch of monomials inducing a basis over here. So the GIs, if you like, give you a basis of the Tiurina algebra. And this gadget, which you can just write down, that's the semi-universal deformation. That's the semi-universal deformation. So by choosing different values of Ti, these are all the nearby singularities. Of course, I should have some kind of germ notation here to make this rigorous. So tau is the dimension of the smooth space of the semi-universal deformation. Now, if you take a general point over here, general values of t, the fiber here will be non-singular. So over general T naught underlined in C tau, the fiber is non-singular, and so it's the Milnor fiber. So, of course, I didn't define Milnor fiber in this general case, but it's as you expect. If we call this map capital F, it's F inverse of T naught, intersect some appropriate ball. Okay, so now the Milnor fiber, in this case, it's some 2n dimensional real manifold, and the boundary is the link of the singularity defined completely as before. So I'm writing this down for n instead of 2 because it's exactly the same. So and mu, of course, as before, is the rank of H2n of m, and you have the same theorem that m is homotopic to n. No, the singularity is n complex dimensions, therefore m has 2n real dimensions. The Milnor
as a bouquet of spheres of
yes.
N is the middle homology.
I know, that's what I'm in the process of. Oh, I'm sorry. Thank you. Yeah, so there's a bouquet of mu n spheres. So it's the same kind of theorem as before. In fact, Milnor proved this version of it. We've just been talking about the case n equals 2. Okay, so that's the meaning of mu, geometric meaning we always knew. Tau is the dimension of the semi-universal deformation, and we have that nice inequality, mu greater than or equal to tau, equality if and only if weighted homogeneous. So let's go up to a slightly harder case, isolated complete intersection singularity. Okay, so I'm not going to define JF. Now you've got B of F1 through F sub capital N minus 2 in C upper capital N, comma 0. So this case is a bit more involved. There isn't any obvious way to write down a JF or a TF, but while we don't have that up there, we still have this geometric interpretation. So again, there exists a smooth semi-universal deformation. You can write it down as we did over here, and the dimension of the base, the dimension of the base, which will it is the length of some X group, X1R, omega 1R, comma R, where R is the local ring. So this is what we're going to call tau. So in this case, I don't have any Tiurina algebra, but I do have a semi-universal deformation. The base space is smooth, tau, which is the length of this algebra, first order deformations. That's what tau is. How about mu? Well, again, M is homotopic to a bouquet of mu n spheres. So, oh, I'm sorry, this should have been n minus capital N minus little n, so that we could get the, so I want to have n complex dimension. So again, M is homotopic to a bouquet of a certain number of these n spheres, where mu is the rank of Hn of M. And this version, which is not in Milner's book, this was proved by Hom a few years later. This involves a bit of work. And what we conclude is that the complete intersection case is similar to the hypersurface case in terms of having two geometrically natural invariants, mu and tau. However, it's not clear what's the relationship. So what's the question? Mu versus tau, how are these numbers related? Well, so tau is the length of this guy, and mu is, well, it's something else. You have to work it out. So it turns out that the same theorem is true. So theorem, mu greater than or equal to tau, mu equal tau, if and only if you're in the quasi-homogeneous case. So this took a long time. Okay, so the names I'll attribute are Groyle, he first proved that if it's quasi-homogeneous, mu equals tau. Okay, that was obvious over here. If it's weighted homogeneous, then it's mu equals tau. It's not at all clear here. So he proved that quasi-homogeneous implies mu equals tau. But other work was done by Groyle and Leuenhoff, gets mentioned in each talk, Steenbrink, and I did something. And finally, Vosegard proved the last. These guys proved that mu is greater than or equal to tau. And Vosegard proved in the general case mu equals tau implies quasi-homogeneous. So the proofs of this are quite intricate. But in any case, in this case analogous to that, you have the inequality, mu greater than or equal to tau, equal if and only if it's quasi-homogeneous. So the question is there anything similar you can say for normal surface singularities? Okay, so we want to look at the NSS case. Now, we've talked about Milnor fibers. If there's a smoothing, semi-universal deformation, you don't have a smooth parameter space. Okay, here we have a smooth parameter space, and so tau is just a dimension. But in general, as I mentioned this morning, when you look at the semi-universal deformation, this number is the dimension of the tangent space of a scheme, not a non-singular space. And in the Pinkham example, we saw there's a three-dimensional component and a one-dimensional component. So how do we get a single tau? Well, first of all, let me just mention a couple of invariants that are going to be useful. So we'll just take a resolution, as we've been doing all along, and I want to consider some resolution invariants, because I'm going to need these for some formulas. So the one idea is going to be that instead of trying to write down relevant numbers like mu and tau in terms of the equations, we're going to write them down in terms of a resolution. Okay? So that might be easier, might be harder, but once you start having lots of equations, you'd have a mess working with them. So the resolution invariants. So first of all, we want to look at some topological ones that come from the graph. And the ones I want to mention are the topological Euler characteristic of the exceptional curve. So what's that? That's, let's see, that would be 1 minus twice the sum of the genera, minus, let's see, the number of loops in the graph, plus the number of EI. So you can read that off from the graph. That's going to be a useful thing. And the other one we want is k dot k, some rational number. So what's k dot k? Well, I've remarked that you can write k as numerically equal to some combination of exceptional curves, where bi is in Q, so that numerically this gives you the adjunction formula. So such that k dot ei is what it should be, 2gi minus 2 minus ei dot ei. So this isn't saying that we're not really doing a canonical divisor. We're not in the Gornstein case. If we were in the Gornstein case, these guys would be integers. So remember, Gornstein case, bi is in z. And we kind of wrote k equals minus then, and we had a polar divisor. But we can write this in general, and therefore we can compute some rational number called k dot k. So some of you might be thinking this is like c1 squared, and this is like c2 in surface theory. Okay, so those are topological invariants we'll deal with. And then how about some analytic resolution invariants? Well, we already mentioned PG, which is H1 of OV twiddle. But since we're going to be deforming, we're going to need to know H1 of theta, which is obviously going to be a very difficult invariant. After all, for a smooth projective surface, Kadeira always complained that you have to deal with this guy, and it's very, very hard to compute. Nonetheless, we can write it down and say that's some resolution invariant. Okay, so what are we going to do with these? Well, let's remember or state some formulas of writing down mu and tau in the isolated complete intersection case. So ICIS formula A. So there's a formula due to Laufer for mu that we mentioned, but this time I'll write it out. 12 PG plus chi top of E plus k dot k. Let's do plus k dot k plus chi top of E. So I had indicated earlier that for hypersurface, Laufer's formula was 12 PG plus something you compute from the graph. And again, those of you who have practice in surface theory can see C1 squared plus C2. And you see the 12 over there, so you're probably thinking of Noether's formula, which is fine. Sorry, 1 plus. So we have this formula for mu. And for tau, there's a formula I proved, which is 10 PG plus 2 k dot k plus our buddy H1 of theta of V twiddle. So these formulas are true. I won't mention yet how you find them in the first place. So now for a general normal surface singularity, how do you define mu and tau? Well, we know already from examples there are lots of smoothings. So you're going to define a number for each smoothing. In fact, for each smoothing component. Okay? So now, suppose F, let me call it, F mapping script V comma 0 into C comma 0 is a smoothing.
In the surface case,
We're in the surface case.
minus 2k squared. Are you sure it's plus and not minus?
Yes. K dot k is a negative number.
Pardon?
K dot k is a negative number. But that's okay. But look, I mean, it's got to be C1 squared plus C2. Because I'll divide by 12, and you have C1 squared plus C2 over 12. Yeah, K dot k is negative because it's negative definite. Okay, so suppose we have a smoothing, and so let's let mu sub f be equal to the Milnor number of the smoothing, and let's let tau sub f be the dimension of the smoothing component. The smoothing component of f. Right, so every smoothing is going to pick out a smoothing component. So these are the numbers that we certainly can look at for a smoothing. And as you move around the smoothing component, well, obviously, tau f will stay the same. The Milnor fiber will be the same. So we have these kinds of things. In order to compare these guys, I mean, we know even looking at the simple Pinkham example that there's going to be some strange relationship between them. So I have to introduce some correction number. So I'm going to define alpha f to be the length of the co-kernel of a certain funny-looking map. I'm going to look at the dualizing module, or rather its dual. So omega of v over c dual, so that's the relative dualizing module. But then I'm going to take its dual. I'm going to restrict to v the special fiber, and then I'm going to look at the dual of the dualizing module for the special fiber. And this length of the co-kernel is what I'm going to call alpha f. So this is a strange looking thing. You know, omega commutes with base change. If you take a relative omega of the whole thing and reduce to the special fiber, pardon me?
It's like the number of critical points. If you have a vibration, this is the number of critical points of the fibers, the contribution to the Euler number.
Okay.
It's always the same number, I think.
Well, for now, let's just say that this is what it is. If I don't have the stars, this restricts exactly to omega v. But when I dualize, this is related to the problem of QGornstein smoothing I was talking about this morning. That things don't. If you take something and then dualize it and restrict, it's not necessarily the same as the restriction dualized. Now, if things are Gornstein, if V in capital V is Gornstein, this is 0 if V is Gornstein, because these are just free modules. Okay, so that means that omega V over C and omega sub V are free of rank 1. But in general, let's look at alpha f, and then we have this theorem. So this is due to me, and again, contribution by the usual gang: Groyle, Steinbrink, Leuencha. I wrote a paper and made some conjectures, proved them in some cases, including complete intersection cases, formulated 3 technical conditions that I couldn't verify, but these guys ultimately proved them. So what's the theorem? And that is that mu sub f minus alpha sub f is equal to some explicit formula on the resolution v twiddle, and tau sub f minus twice alpha f is again some explicit formula. So I put this sub f there because f's the name of the smoothing. This stuff is this is just stuff that really belongs to the resolution, hence to V. So what's a corollary? So if V is Gornstein, then alpha f equals 0. So mu and tau are independent of the smoothing. V Gornstein and then for every smoothing, mu and tau are the same. Right, because this is 0, so mu f, it's some explicit formula. So if you have a different smoothing, you have the same formula. So it also follows that in the Gornstein case that those are actual formulae for mu and tau, and the above formulae are true. So here they were just true in the complete intersection case, but actually they're true for Gornstein singularities. Okay, so the theorem that I proved was that if V is Gornstein, then mu is greater than or equal to tau, and mu equals tau if and only if it's quasi-homogeneous. So this is fairly old result. This is something done in the 80s. So notice that I left something off here. I didn't say this had to be smoothable. In fact, what I can do is say I can define mu and tau whether it's smoothable or not. There's the formula. So need not be smoothable. So what I'm doing is the following. I'm saying, let's look at this formula. Alpha f is 0, and alpha f is 0 because I'm in the Gornstein case. And so I have an explicit formula for mu. It reduces to that. For tau, it reduces to that. I can then write down mu minus tau. Forget about whether it's smoothable. Just write down mu minus tau. You may get some negative expression for both mu and tau, but nonetheless, you'll find this out. Okay, so what's the difficulty in doing this? What's the difficulty in it? The difficulty is h1 of theta. I mean, that's got to be the most difficult thing to compute in a problem like this. But remember that on a surface, theta is isomorphic to omega 1 tensored k dual, I guess. So in the Gornstein case, k is some exceptional divisor. So in the Gornstein case, this is omega 1 of z. Now the advantage of having things in terms of omega 1 instead of theta is you have some Poincare complex. You can differentiate, go from O to omega 1 to omega 2. So you use some Poincare complex. So that'll get you started. And I should mention Steinbrink over here too, because he had done some related work that was useful. So that's why you have a chance of doing something with inequalities. How do you prove something's quasi-homogeneous? Well, you basically follow an idea not of Saito, but of Kunz and... Yes?
You take a derivation, then you take the exponential of the derivation. How do you prove that the one parameter subgroup is
no, I mean, there's some work to do. I mean, Saito really has a theorem. And Ashea and Viba, some commutative algebraists, kind of just examined that point of the derivation. If you have a derivation and you know how it acts on the tangent space m mod m squared. Okay? Then under certain conditions you can tell when it's weighted homogeneous, whether you can basically diagonalize it and make it an Euler derivation. So with that in mind, what you had to do over here is if mu equals tau, you have to produce a derivation. So there's kind of the inequality, and then if the difference between mu and tau, if all those terms are 0, you have to produce a derivation. So I'll just say produce a derivation. So here's a completely satisfactory answer to the original question for a Gornstein surface, and it doesn't have to be smoothable. You just say, okay, mu is this number, tau is that number. It's not smoothable, so I don't have a Milnor number. No smoothing component, but nonetheless, I have a compatible definition, and I can end up with this theorem. So the goal is to be able to handle the non-Gornstein case. So I'll just say non-Gornstein question mark. So we shouldn't make fun of the non-Gornstein case. I mean, rational singularities are all over the place. There are plenty of weighted homogeneous singularities. So here's a proposition.
So what is the u and what is the c?
Excuse me?
What is the u and what is the c?
So here K is isomorphic to O of minus Z. So we mentioned that in the Gornstein case, on the resolution, you look where the non-zero 2 form, it extends over the exceptional divisors with poles, and this is the polar divisor. So this, of course, is on V twiddle. Everything's on resolution. And I'm just saying this is much easier to work with than this, or this. And you can only do that in the Gornstein case. So in the proposition, let's just put together the... it's really a corollary of this. You write out the terms, and what do you get? So suppose f of v into 0 into c0 is a smoothing. Is a smoothing of capital V. So I'm going to let S contained in theta v twiddle be the sheaf that's usually written as omega 1 v log e, omega 1 v twiddle log e dual. So this is the bundle of derivations logarithmic along E. So form is logarithmic along E if x equals 0 with Z, you allow dx over x. This is the dual of that. So E is the reduced exceptional divisor, and it's got normal crossings. So this is a vector bundle. It's a nice vector bundle. This is kind of equally difficult to work with. H1 of that is H1 of theta, but nonetheless it has some geometric meaning. So here's the statement then. So I'm going to put together stuff from here, things I didn't write down. 1 plus mu sub f minus tau sub f plus this annoying alpha sub f is equal to H1 of the structure sheaf of V twiddle minus H1 of this guy S plus H2 of H1 of wedge 2 of S, which you can work out to be H1 of minus K minus E. I would say minus K plus E. So what's going on here? Well, this is just, as I say, a corollary of that. I didn't say what these terms were, but you plug them in, and this difference here, remember we're kind of thinking about about mu minus tau. Let me just rewrite this term here. This is summation minus 1 to the I h1 of wedge I of s. Goes from 0 to 2. So it's a strange sort of thing. And I've simply remarked here that the determinant of this bundle is k plus e, so the determinant of its dual is minus k plus e. So let's hold off on the left side for a while and look at this funny looking thing. And now I have a quiz problem for experts on surface theory. So suppose X is a projective non-singular surface, and say script F is a rank 2 vector bundle. Suppose I look at summation minus 1 to the I Euler characteristic of wedge I of F. I goes from 0 to 2. I mean, I did the same thing over here, but here I just had an H1. But here I'll take Euler characteristics. This is wedge 0.
Oh, wedge 0.
Yeah, so this is wedge 0. This is wedge 1. This is wedge 2. What's that equal to? Anyone? Can anyone do Riemann Roch quickly? It's the second year in class. So what that has to do with this, I'm not sure, because I'm going to state a conjecture, which I can't prove. But in any case, you shouldn't think of this as being that weird, perhaps. So keeping in mind that we want a conjecture, and B, we'd like to have something that doesn't depend upon smoothings, or even existence of smoothings, but only depends on the singularity. The right-hand side only depends on the singularity. If it smooths, then it's related to mu and tau, which have geometric meaning, and then this silly thing, alpha over here, that we have to throw in. So now we have our big conjecture. So part A says if v comma 0 is Gornstein, then the right-hand side, this term over here, is greater than or equal to 1, and equal to 1 if and only if quasi-homogeneous. And part B says if v comma 0 is not Gornstein, then the right-hand side is greater than or equal to 0, and equal to 0 if and only if quasi-homogeneous. Does part A.
No, in the middle part.
Oh.
The binary number minus alpha f and also binary number minus 2 alpha or plus 1 alpha.
Pardon me, over here?
Both are minus.
But this is minus and this is minus twice. So you can see it. If you take mu minus tau, if you take this and subtract that,
Okay, I see. Yes.
and then add it in, then the it should be independent of the you know it's independent of the smoothing, but you play around with the right hand side.
I understand if it's quasi-homogeneous, it's either 0 or 1. So
Okay.
I don't understand this.
Let's talk about the conjecture, okay? So first of all, A is...
Not Gornstein.
Yeah. So remark...
Quasi-homogeneous, I think it's Gornstein.
No. A is proved. That's this. See, if A, it says mu is greater than or equal to tau, and equal to tau if and only if. Now, if it's Gornstein, the alpha part is 0. So the left-hand side is 1 plus mu minus tau. Okay, so the left-hand side is 1 minus mu plus tau. Yeah, so we don't even have to bother with the right-hand side. 1 minus mu plus tau, and so that's greater than or equal to 1 by this theorem. So part A of the conjecture is fine.
I don't understand. Quasi-homogeneous, I thought must be, it's a complete intersection. No.
Just needs to cease action.
Quasi-homogeneous is, I mean,
Just sister action, okay.
you take a cyclic quotient singularity, boy, those are quasi-homogeneous.
Okay, sorry.
Okay, so also for part B, this direction is true. For B, quasi-homogeneous implies that the right-hand side is 0. So that's also a theorem. It's not that hard a theorem. But being quasi-homogeneous for a normal surface singularity that's not Gornstein, you've got to distinguish between the Gornstein and non-Gornstein cases. And there's a way to see that if you just take the cone over the canonical curve, or the cone over any line bundle, some power of which is the canonical bundle. You can experiment in that good case and see why there's a difference over here. Okay, so what you have to do here is, in the quasi-homogeneous case, you don't worry about the fact that that this guy is not an invertible sheaf. You have a nice section of this. In the quasi-homogeneous case, so remark, quasi-homogeneous implies there exists an Euler derivation, which is actually in, if you examine it, H0 of S. So immediately you have a section 0 OV into this sky S, and in fact on the minimal good resolution this is exact. So this is D, and if you like, this is wedge D. So where does that leave us? That leaves us in wondering whether, in the non-Gornstein case, whether you have an inequality and whether equality implies quasi-homogeneity. Okay, so before I go on with this, we're talking about normal surfaces. But if you talk about reduced curves, which maybe you would like to have mastered first, Greuel years ago had some similar conjectures for curves. Conjecture for curves. Okay, so for curves, as here, you've got to figure out what mu means. So he did that in a paper with Buchweitz. If it smooths, yeah, there's already a good meaning for it, but you make a general one. Tau, he has dimension of the smoothing component, but there was a formula that Deligne gave for that, and you can just use that formula as the definition of tau, whether or not the thing smooths. So you can try and formulate a similar conjecture, and his conjecture says mu minus, what is it? Tau plus 1 minus t.
You write the conjecture and A, and then you say that A is proven, so it's not a conjecture.
Right. But, so I can just move the conjecture down to this part. But I wanted to write these things next to each other so that you could see the similarity and the difference. Okay, so the conjecture says that this guy is greater than or equal to 0 and equals 0 if and only if quasi-homogeneous. And this guy here is what's called the type. So that has to do with taking a minimal resolution of the singularity, and type 1 is what Gornstein means. And so t is greater than or equal to 1, and it's equal to 1 if and only if it's Gornstein. And this is okay for Gornstein or quasi-homogeneous. So structurally, the shape of the conjecture and where it sits, how much is known, is very similar to this one. Okay, so I warned you that rational surface singularities are a zoo, and you'd have to be lucky to prove something for all normal surface singularity. Here we're kind of lucky to have this for Gornstein ones, but for non-Gornstein ones, we basically want to break this conjecture up into some cases that are plausible, where at least we might figure out whether it's right or wrong, like rational singularities. So why don't we do that? So we'll break this up. How about, so for check in special cases. So let's see, do I want to do rational first? Yeah, so what's this mean in the rational case? So, rational conjecture. So that would say if V common 0 is a rational surface singularity, then, well, now the H1 of O is 0. Then H1 of S of V twiddle is less than or equal to H1 of minus Ks of V twiddle plus E. So that's what the conjecture states, and equal if and only if quasi-homogeneous.
Can I say something? You wrote like G and then wedge D, and then you wrote 0, but actually it's a finite, basically kernel, which is exactly the formula which you have above for C2 of F, because it's where the vector field.
No, this is right. This is fine.
Why is it you're claiming it's exact?
I'm claiming it's exact. Yeah, no, I mean it's not completely, it's not obvious. It's not obvious. It turns out,
So this implies
because I didn't write it as a section of theta. I wrote it as a section of logarithmic theta.
Right.
That's why. So if you look at it locally, you'll see that in fact it's a section of the bundle. Yeah, so Fabrizio was saying that if I put a theta v in here, all the derivations, then there's a co-kernel. This isn't exact. Okay, so so these have some meaning, these two numbers. So this guy, just as H1 of theta means deformations of the resolution, this means deformations of the resolution that keep all the all the exceptional curves. So H1 of SV twiddle equals dimension of the space of equisingular deformations of the resolution, which by blowing down is equal to equisingular deformations of equals dimension of space of equisingular deformations of V. You just blow down. So while we talked about moduli spaces being schemes with nilpotents and all that stuff, for rational singularity, if you just look at the equisingular deformations, that's a nice smooth space. Problem is, how do you compute its dimension? Well, it doesn't just depend on the graph. If you see in the graph that there's a parameter because of a cross ratio, yeah, you can contribute to it that way. But there are far more subtle contributions that are very hard to see. And in fact, for the same graph, you can have lots of different values. For same gamma, you can have many different values. So, I mean, already in Kodaira-Spencer theory, you see this, it's called jump phenomenon. Okay, so this guy, on the other hand, this is topological. Turns out to be topological. And this is called the second plurigenus by I think Kimio Watanabe. You can give an algorithm to compute that given the graph. So this is giving you some topological upper bound on the number of equisingular deformations. So that's what the rational conjecture means. And I'll just say that there are some partial results. So partial results. One, so it's okay if gamma is star-shaped. So a star-shaped rational singularity, not taught. In general, there can be lots of analytic structures, may not be weighted homogeneous. Nonetheless, you can check that this is true. This could be a very big number, but you can prove exactly it's less than or equal to this with equality if and only if weighted homogeneous. So yeah, so that case can do. Two, it's okay if H1 of S is 0. That's a so-called taught case, but even not necessarily the taught case. Well, the only thing to prove there is that if this is 0, and this is 0, and it's not weighted homogeneous, and this is positive. So that's not too hard. You can prove that. And 3, I'll just say it's consistent with a non-trivial case where 1's less than or equal to 2 is what comes out for some non-quasi-homogeneous singularity. So I should say that this guy is very hard to compute. So the achievement over here is writing down some graph with 2 nodes and being able to prove that H1 of S is 1. For in this particular case, H1 of S is 1, but this second guy is 2, and this is patently not star-shaped. Let me finish with another example. If you're looking for cases where you have a shot at proving this, you might want to look not at the right-hand side, but the left-hand side. And the left-hand side is going to be a mess unless this is 0. So remember we talked about QGornstein smoothings? So not only is alpha equal to 0 if the singularity is Gornstein, but for a QGornstein smoothing, alpha f is 0. So let's see how that helps us. For a QGornstein smoothing, you see, for a QGornstein singularity, this guy is some tensor power of omega v, because this has finite order. And so this is, if omega v bracket n is trivial, then omega v twiddle, then omega v twiddle a dual is just omega v twiddle upper n minus 1. So in a QGornstein smoothing, these guys vary nicely. So that means this is 0 in the QGornstein case, for a QGornstein smoothing. So we have the QGornstein conjecture. So here's the conjecture for a QGornstein smoothing. Alpha f is 0, so mu and tau are defined, and mu is greater than or equal to tau QGornstein, non-Gornstein. So it should say mu is greater than or equal to tau plus 1 with equality if and only if quasi-homogeneous. Actually, I think this should have been a minus sign. You can check that. You can check your notes to get rid of the alpha f. I think I had to put a minus there. So for QGornstein smoothing, mu should be greater than or equal to tau plus 1. So with equality if and only if it's quasi-homogeneous. So let's see if I have the numbers right. No, it's mu greater than or equal to tau minus 1. Sorry. So let's think about the Pinkham example where you had mu equals 0, and it's a one-dimensional smoothing component. Yeah, mu is 0 and tau is 1. So, so this would be the conjecture, and I'll mention a theorem. So one way to make QGornstein smoothings is by quotient smoothings. So that's where we have a group acting freely on C3 off the origin. We had F, a polynomial, which was invariant under the action of H. And we were interested in the special case where the Milnor number was close to the order of the group to get QHD smoothings. But you can make, you can forget about that just to make QGornstein smoothings that aren't QHD. So the theorem is, suppose H contained in, let's do in GL n plus 1C, acts freely off the origin, and F is H invariant with isolated singularity. So I'm going to state a result here that's true for any number of variables, not just for 2. So then the induced QGornstein smoothing of V bar, which is F equals 0 mod H, satisfies well, we have to distinguish two cases. The equivalent of the Gornstein case, which is that H is contained in SLN. Mu bar is greater than or equal to tau bar with equality if and only if F is quasi-homogeneous. And 2, H is not contained in SLN plus 1, then mu bar is greater than or equal to tau bar minus 1, again with equality if and only if F is quasi-homogeneous. So in fact, this is, for n equals 2, this is what I'm talking about over there. I just mentioned this case over here because you can actually prove this in the same way. So the proof of this is kind of interesting, I think. Let me mention what the main ingredients are in this. So first of all, I've been throwing around this tau, and I even mentioned a formula for it in the isolated complete intersection case.
So mu bar is just mu f for this movement.
It's for V bar. So it turns out, because the action of the Milnor fiber is free, the quotient of the usual Milnor fiber, that's a bouquet of spheres, that only has homology in dimension n, and the rank of that homology you call mu bar. Okay? And then tau bar is going to be the dimension of the smoothing component in the corresponding smoothing component for that semi-universal deformation. So one of the important things to do was get some understanding how in the world do you compute the dimension of a smoothing component. Okay, because dimension of T1, you know, maybe that's hard, but that's just the tangent space. So, so what you do to compute the dimension of the smoothing component, well, I don't think I'm going to be able to show you, is you find out if you change these bundles over here to the relative tangent bundle, theta of V over C, and this to theta of V, and you look at the length of the co-kernel, that's the dimension of the smoothing component. So this is a very surprising result. So this is true anytime you deform a singularity. You have a smoothing, it lies on some smoothing component. You can compute what the dimension of that is just from that one parameter family by computing with this theta and this theta. And look at the length of the co-kernel. That's the dimension of the smoothing component. So in order to prove this, this result, there are several ingredients. That's one of them. So you have a hold of a tau bar. Another ingredient is understanding the G acts, in this case, on the Jacobian and Turina algebras. I don't know whether I erased it. Yeah. In that case, G acts on this, and it acts on this. And so you have to figure out how those invariants downstairs are related to the action of G on these two algebras. So you can ask yourself the question, what is the action of G on this guy? So you have a cyclic group, even. How does this decompose into the characters? How big are the isotypic components for the action of G? And you have to work that out. And there are two ingredients for that. One of them is a result of Terry-Wahl that relates the G action of this to the G action on the homology. These guys have the same dimension, but the G action is different. There's a geometric action over here and an algebraic action here. So Terry-Wahl has a result that says, well, the G action over here and the G action here differ by the determinant character of G. By the determinant character of G, which is going to involve these two things that are different. Finally, what's the G action on here? What's the G action on the whole cohomology ring of M? And it turns out it's very simple in the even-dimensional case using the Lefschetz fixed point theorem. So you kind of have to throw that in, and then you put it in and you stir it together, and you end up with this. So I'll stop.